Alright, we're back. We're going to do section B now, so let's get to it. Question 1. A particle of mass m and charge q travelling at velocity v enters a uniform magnetic field B as shown in figure 1. Is the charge q positive or negative? Give a reason for your answer. So, this should probably be 2 marks. I mean, you could probably just, well, keep it 1 mark. You could just guess the answer and get it right. That's not proper physics. Alright, so we've got a particle. It enters the magnetic field here. The magnetic field is into the page. So we're going to use our right hand slap rule to see which direction a positive charge would travel. And if it doesn't follow the direction shown, then obviously the charge has to be negative. So get your right hand, point your fingers away from you, and point your thumb to the right, because that's the direction of travel. Your palm should be pointing upwards, which means if this was a positive charge, then it would curve upwards, but it's not. It's curving downwards, so that means it is negative. So we'll say negative. Okay. And you could just say, geez, I don't even know how you'd phrase this in one line. Just say, according to right hand slap rule, a positive charge would move up. There you go. According to right hand slap rule, a positive charge would curve up. Okay. It's actually hard to allocate a mark to exactly what they would want there, but I think negative and the fact that you've mentioned right hand slap rule should be enough. Part B, explain why the path of the particle is an arc of a circle while the particle is in a magnetic field. Okay, so why is it in an arc of a circle? Well, we assume that because it's traveling at a constant speed, the magnetic force on this particle will provide a constant force. And that force is going to be perpendicular to its speed. And so whenever you've got a force perpendicular to a velocity, you're going to be creating circular motion, which is why this is part of a circular arc. Okay, so you can just mention something along the lines of force is always perpendicular to velocity, and I guess you would also say because velocity is constant. I won't say velocity is constant because the velocity changes throughout the motion, but the magnitude is the same. So because speed is constant, force is constant. Therefore, centripetal acceleration causes circular motion. There you go. I think that should be okay. Let's have a look at the exam report. So section B, there it is. Okay, yeah, so part A was negative. Part B, here we go. The force applied to the particle would always be at right angles to the direction of motion. We've stated that. And the force would be constant in magnitude. Yep, we stated that. Both of these conditions are required to explain the circular motion identified in the question stem. We did that. Let's keep going. Alright, question 2. Figure 2 shows 2 equal positive stationary point charges placed near each other. Sketch on figure 2 the shape and direction of the electric field lines. Use at least 8 field lines. Okay, so you've got 2 positive charges near each other. So that's going to cause like the field lines to bend. You know, that you've all seen the picture of what 2 positive charges field lines look like. So they're going to come out of the charges, going to look something like this. So that's 1, 2, 3, 4. Okay, and then you just draw another 4 like on the other sides. So you're just going to draw one out there, one out there, one out there, one out there. Don't have to be too precise. It's the ones in the middle they're probably looking at them, that you know what's going on there. The ones on these edges you can be less precise about how they sort of curve off. So in terms of what this report has, there you go. So pretty much what we've got there. Cool. All right. Question 3. Figure 3 shows a schematic diagram of a DC motor. The motor has a coil, JKLM, consisting of 100 turns. Make a note there, that is N. The permanent magnets provide a uniform magnetic field of 0.45 Tesla. The commutator connects X and Y. The commutator connectors X and Y provide a constant DC current to the coil. The length of side JK is 5 centimeters. Alright, current I flows in the direction shown in the diagram. But which terminal of the commutator is connected to the positive terminal of the current supply? Okay, well, current comes out of the positive terminal of the battery. So if your current is currently going here, then it's connected to X, right? So that's all you got to say. 50-50. Part B, draw an arrow on figure 3 to indicate the direction of the magnetic force acting on side JK. Okay, so this we've got to use our slap rule. So we've got current flowing this way, so that's like away from us, I guess. Field lines go out of north and into south, so you get your right hand, you have to point your thumb away from you and your fingers to the right, and your palm should be facing downwards. It's a bit of an awkward way to do this setup, but your palm should be facing downwards. So the arrow, if I get rid of this one, draw an arrow on figure 3 to indicate the direction of the force. Well, that'll just be pointing down like that. I think that's all they want, just an arrow pointing down. There you go. Alright, 3C, explain the role, explain the role of the commutator in the operation of the DC motor. Okay, well, the whole point of the commutator is so that it reverses the direction of the current every half turn, I guess, so that your force on each side of the coil like swaps every half turn in order to produce that torque that pulls it around in a loop. So I think that's all they really want you to say. I'll just write it out. So commutator reverses current in the coil every half turn. This is to change the direction of force on the sides of the coil to ensure it continues rotating. I think that's all they're really looking for there. Let's have a look. So the purpose of the commutator is to reverse the direction of the current every half turn to keep the motor rotating. Some students stated that the current is reversed every half turn but could not continue with a clear reason. Students who did not refer to the current reversal every half turn generally responded in a way that indicated they did not understand the question. There you go. Alright, part Part D, a current of 6 amps flows through the 100 turns of the coil. The side JK is 5 centimeters in length. Calculate the size of the magnetic force on the side JK in the orientation shown in figure 3. Okay, so it's asking for magnetic force in a magnetic force on a current in a wire. That is just F equals N B I L. N is the number of turns, B is the magnetic field strength, I is the current, and L is the length of the wire in the field. So, what was B? 0.45 Tesla. Okay, 0.45 Tesla. Right, so we've got 100 turns times 0.45 times current, which is now 6 amps, times the length of wire in the field, which is 5 centimeters. Side JK is perpendicular, isn't it? Yes, okay. There's only a force if your current is perpendicular to the field. So that's true here. So that's 0.05 meters. Calculate a time. We've got 100 times 0.45 times 6 times 0.05. 13.5. There we go. Done. Question 4. Assume that a journey from approximately 2 Earth radii down to the center of Earth is possible. The radius of Earth RE is 6.37 times 10 to the 6 meters. Assume that Earth is a sphere of constant density. A graph of gravitational field strength versus distance from the center of Earth is shown in figure 4. What is the numerical value of y? Y is this value here, which is the gravitational field strength at 1 Earth radius. So that means that that's just normal g, which is, we're assuming 9.8 because of the instructions to part B. Take the value of g to be 9.8. So that's all that is. I think the trick there was identifying that that location is the surface of the Earth. Part B, explain why gravitational field strength is 0 at the center of the Earth. So right there, we're right at the center of the Earth. I guess one way to think about this is that if you imagine the Earth as being not made of like atoms, but large balls, I guess, okay? And the simplest way I can do this is just start thinking in one dimension. So one-dimensionally, you have some mass here, some mass here, you're right in the middle. What's the gravitational field right in the middle? It's going to be 0, because the gravitational fields of either of those two things cancel out. If you think two-dimensionally, okay, you stick another one here and here. Now all of these balls have the same mass, but right in the center, the gravitational fields from each of them combined just cancels out to be 0. Now if you start thinking three-dimensionally, alright, and you just add like a whole bunch of balls around that are all, there's always a ball that can be paired off with another ball exactly the same distance but on the opposite side. The gravitational field from each of those masses will cancel out. Okay, so I guess you could just say that the sum of the gravitational field provided by all of the mass in Earth just cancels out to be 0. So yeah, I mean, you know what, we'll see what the report says. Maybe I can just refer you to that. Students were required to indicate that the vector sum of the gravitational fields caused by all the mass of Earth is 0. That's what we were talking about there with the diagram. Students could do this by indicating that at the center of the Earth there are equal masses in all directions, or that the gravitational attraction from one direction is balanced by an equal attraction from the opposite direction. There were 2 common errors worthy of note. The first was to attempt to apply that and state that as r approaches 0, f approaches 0. Well, that's wrong. If r becomes 0, f becomes infinity. The second was to represent the net gravitational field as a circle with radial arrows drawn to the center and the statement that they all cancel out. No, that's not what I did. That's a different thing. This suggested that students either felt gravity was a repulsive force that pushes towards the center of the Earth, or that it is not the mass of the Earth in it, but rather some object or region at the very core that is the source of the gravitational field. This is actually a really nice problem that you can do using some calculus. It's out of the scope of the course, but yeah, it does show you why it drops off linearly. But I'll just say, what am I doing? R equals. I'll just say refer to report. There we go. Right, for C, calculate the increase in potential energy for a 75 kilogram person hypothetically moving from the center of Earth to the surface of the Earth. Show your working. Alright, so we have a graph of field strength versus distance, and we know that the area under the graph times mass times the mass of the object that's moving will give us the change in gravitational potential energy. So that's a nice triangle. So it's we'll say change in gravitational potential energy equals area times mass of person. Okay, so they're going from the center to the surface, so we want this area here of this triangular shape. And that's just half times base times height. So the height there is 9.8, the base is the radius of the Earth. Okay, so half times 6.37 times 10 to the 6 times 9.8, so that's the area of the triangle, and then the mass of the person is 75. So multiplying all that together, we will get half times 6.37 times 10 to the 6 times 9.8 times 75. Big number, let's put in scientific, so 2.34, just go to 2.3 times 10 to the 9. And there we go. Alright, question 5. Navigation in vehicles or on mobile phones uses a network of global positioning system satellites. The GPS consists of 31 satellites that orbit Earth. In December 2018, one satellite of mass 2,270 kilograms from the GPS block whatever was launched into circular orbit at an altitude of 20 kilometers above Earth's surface. Identify the type or types of force or forces acting on the satellite and the direction or directions in which the force or forces must act to keep the satellite orbiting Earth. Okay, you're in space. Okay, we're assuming there's no like dust and stuff, there's no friction, so you're orbiting Earth. There's only one force acting on you, which is gravity. Okay, so only force is gravity. Only force is gravity. Okay, so that's identify the type of forces and the direction. Okay, only force is gravity. Gravitational force acts towards Earth's center. That's all you got to say. There's 2 marks, one for the type of force, one for the direction. Part B. Calculate the period of the satellite to 3 significant figures. You may use data from the table below in your calculations. Show your working. Okay, so in the previous exams, I've already mentioned you should have this formula handy. R cubed over T squared equals GM over 4 pi squared. I haven't actually read through the data, so we might not even need to use this, but I guess you can only use, if you don't have how fast the satellite's orbiting, you have to use this formula. I don't think there would be another way to do it, which we don't have the speed of the satellite, so we're going to have to use this one. All right. Now t is the period, so we're solving for t. T equals the square root of, it's going to be 4 pi squared times r cubed over gm. We've got r, so the radius of the orbit, have it, but we can work it out. So it's given us the altitude of the orbit and the radius of the Earth. So the radius of the orbit is going to be those two things added together. And then we just chuck it all in. So 4 pi squared times total orbital radius, which is 6.37 times 10 to the 6 meters, plus 2 times 10 to the 7. Don't forget to cube this, because it's r cubed. And then all of that over 6.67 times 10 to the negative 11 times the mass of the thing you're orbiting, which is Earth. So 5.98 times 10 to the 24. Alright, bunch of calculations. So square root of 4 pi squared times 6.37 to the 6 plus 2 times 10 to the 7. Don't forget to cube that over 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. Hope I've typed everything in right. My squared pi, yep. Okay, 426, so 4.26 times 10 to the, that'll be the 4th power. And that's it. Alright, let's go have a look at the report. Alright, so this was question 5. Okay, so for the first one, yep, the only force is gravity, and it acts towards the center of the Earth. Yep, we got all that. Second question, period. Yep, so they just use that formula. There you go. Ooh, did it say significant figures? Yes, 3 significant figures. Cool. I forgot that. I'll highlight that for future reference. There we go. Alright, anytime it's got significant figures, just highlight that. Put a big circle around it or something, because you don't want to lose a mark for not putting significant figures. Luckily, I did put my 3 significant figures, but I wasn't paying attention, so could have lost a mark there. Question 6. Alright, a homeowner on a large property creates a backyard entertainment area. The entertainment area has a low voltage lighting system. To operate correctly, the lighting system requires a voltage of 12 volts RMS. The lighting system has a resistance of 12 ohms. Calculate the power drawn by the lighting system. So there's not much information to go on here, but here it says that to operate correctly, it uses up 12 volts, and it has a resistance of 12 ohms. So the only way to calculate power here would be power used is voltage squared. So the voltage used squared divided by the resistance. So 12 squared over 12 is just 12. Use your calculator to double check if you're not confident. To operate the lighting system, the homeowner installs an ideal transformer at the house to reduce the voltage from 240 volts to 12 volts RMS. The homeowner then runs a 200 meter long heavy-duty outdoor extension lead, which has a total resistance of 3 ohms from the transformer to the entertainment area. The lights are a little dimmer than expected in the entertainment area. Give one possible reason for this and support your answer with calculations. Okay, so why would the lights be dimmer? Well, you could probably make an argument in a couple of ways. So by having this long heavy-duty extension cord, which has resistance, that's using some of the available power or voltage. Some of that available 12 volts is being drawn by the heavy-duty leads. So there's less voltage available, I guess you could say, to the lights, and that's why they appear dimmer. You could use the same argument for power as well. So I think we'll just state that. Sorry. So we'll say, how are we going to do this one? Let's do let's talk about voltage. Actually, no, power, because should we do power or voltage? I think I might do. Sorry for the dead air here. I think I might just do. Which one do I want to do? I'll just do voltage. Doesn't really matter. All right. So the light system operates correctly at 12 volts, but it has a resistance of 12. Okay. So the resistance of 12 for the lights. You've also got a resistance of 3 for the power lines. So the total resistance, assuming everything's in series here, is 12 plus 3, which is 15 ohms. Okay, now this 15 ohms of total resistance uses up all of this 12 volts that have been transformed, and so you could work out the current, I guess, if you wanted to. So we could say the current of this whole system is equal to total voltage used up divided by total resistance. So that's 12 over 15, which is 0.8 amps. Sorry if I am pausing a lot and thinking, because I'm trying to do this blind, just to sort of show you my thought process, as with all exams that I'm putting up on here. So that's the current that's in this part of the system, and then we could say that, well, now I know the current going through the lights. What is the voltage being used up by the lights? So the voltage of the lights is just the current through them times their resistance, which is 0.8 times 12, which is, what's that? 0.8 times 12, 9.6. So now with these extension cords, the lights are only getting 9.6 volts instead of the 12 that are required for them to work properly. So now that you've worked out how much voltage is going through them, then you can say the lights receive less voltage than when operating correctly. Did I just write when twice? When operating correctly. Okay, there we go. Using the same equipment, what changes could the homeowner make to improve the brightness of the lights? Explain your answer. So here it says that they've got a transformer that steps down the voltage, but then they run this cable from the transformer to the entertainment area. So one thing that they could do is maybe move, so maybe if I draw a picture, so here's your voltage source, okay, then you connect that to your transformer, and that's a step down, and then that connects directly to the light globe. Okay, so all of this is using up some of that transformed 12 volts. So one thing you could do is just move the transformer closer to the globe. Right, so instead of it being where the voltage source is, you move the transformer here so that you've got all this lead to use up a little bit of the 240, which shouldn't be that much. It should be only like 3 volts or something, and then you've got like 236 going into the transformer, and then it steps down to like 11 point something volts. So moving the transformer closer to entertainment area, that would have the effect of, I guess, how would I phrase that? It would have the effect of current. So because we're moving the transmission wires on the other side of the transformer now, so that means current in the power leads, is smaller, leading to less power loss. I think that makes sense. All right, how are we going for time? So 30 minutes. Pause here, go get a drink, and then we'll do a few more questions. All right, question 7. Students in a physics practical class investigate the piece of electrical equipment shown in figure 5. It consists of a single rectangular loop of wire that can be rotated within a uniform magnetic field. The loop has dimensions that and is connected to the output terminals with slip rings. The loop is in a uniform magnetic field of strength 0.4 Tesla. All right. Part A, circle the name that best describes the piece of electrical equipment shown in figure 5. So the whole thing is called a watt. So we're connected to slip rings. This says output, not input. So it means we're generating electricity. And the fact that we've got slip rings means it's an alternating current that we're generating. So that means we circle alternator. I think a lot of people would probably also choose AC motor for some reason. Probably because they got confused. Are we generating or are we like inputting electricity into this to make it turn? So just be careful with that. All right. What is the magnitude of, sorry, let me start again. Part B, what is the magnitude of the flux through the loop when it is in the position shown in figure 5? So how much field is going through the loop? None. So the magnetic flux is 0. Okay. How would you explain that? You just say no field, maybe no magnetic field. No magnetic field passes through the loop, or the loop's area. I think that's okay. Or you could just say it's like parallel to the magnetic field or something like that. Okay, the students connect the output terminals of the piece of electrical equipment to an oscilloscope. One student rotates the loop at a constant rate of 20 revolutions per second, so that's a frequency. Calculate the period of rotation. So period and frequency are inversely proportional to one another, so period equals 1 over 20, which is 0.05. Done. D, calculate the maximum flux through the loop. Show you working. So if it was to rotate 90 degrees, then the flux would be a maximum, and flux is just field strength times area. So field strength is 0.4, and we've got 0.5 times 2.5 for area. So flux equals field strength times area. Can't remember the numbers. 0.4 times 0.5 times 0.25. Okay, so that's the field strength. This is working out the area of the loop. We get 0.4 times 0.5 times 0.25. 0.05 Webers. Right, part E. The loop starts in the position shown in figure 5. What is the average voltage measured across the output terminals for the first quarter turn? So quarter turn means that the time of this rotation is 1/4 of our period. So 1/4 of 0.05. Show you working. All right, so average EMF is equal to negative N times change in flux over change in time. N, how many turns do we have? it's a single rectangular loop, so that's 1. Don't worry about the negative for now. 1 times change in flux, well, it goes from 0 flux to maximum flux in a quarter of a rotation. That maximum flux is 0.05, so that's going to be 0.05 on top. And then underneath, we're going to have the time it takes for it to do that, which is 1/4 of 0.05. So 1/4 times 0.05. Now I can do some quick sort of calculations by cancelling some stuff out here. So it's going to be 0.05 cancelled out with this one. It's 1 times 1/4, which should be 4. But you can check that on your calculator. I'm not going to waste time typing it in. So 4 volts. That's that. Part F, state 2 ways that the amplitude of the voltage across the output terminals can be increased. So again, according to Faraday's law here, you could increase the amplitude of the voltage by either increasing the number of turns of the coil, assuming we have the available materials to do that. We could increase the flux, so we could increase the flux by either increasing the field strength or increasing the area of the coil, or we could decrease this number here. The smaller your denominator is, the larger the fraction is overall. So we could rotate the loop faster. That would produce a decrease in delta T here. So one of either increase n, so increase number of turns, increase magnetic field, increase loop area, whoops, or decrease period / increase rotation speed. There we go. So either of those, so 2 of those options, I guess you could say. All right. Part G. Figure 6 shows the output voltage graph shown on the oscilloscope for 2 cycles. Cool. The students now replace the slip rings with a split ring commutator. On figure 7, sketch with a solid line the output that the students will now observe on the oscilloscope. Show 2 complete revolutions. The original output is shown with a dashed line. Okay, so we've changed the slip rings to a split ring commutator. All that happens to do is change these bottom negative parts of your voltage graph and turn them into positive. And so it looks like a bumpy graph. So it's going to look something like this. Okay. I guess you could also flip the positive parts down into the negative and you'd still get this like a correct answer, but I prefer flipping the negative ones up to the positive. Cool, so that's it for that question. Let's go back and look at the report. Okay, so 7A, device is an alternator, good. Part B, I, the flux is 0 because there's no flux, there's no field going through the loop, parallel, that's what we've said. Part C, period of rotation was 0.05, that's 1/20. Part D, maximum flux, same calculation as we have. Part E, again just using Faraday's law, 4 volts. And part F, 2 of the following options, which are pretty much what we've written down. And question G, yeah, it's that bumpy graph that they're looking for there. Cool. Okay. Question 8, a 250-gram toy car performs a loop in the apparatus shown. Alright, so it goes down a hill of height h, and then it does a loop in this 40-centimeter diameter circle. The car starts from rest at point A, so It's not moving when we release it, and it travels along the track without any air resistance or retarding frictional forces. The radius of the car's path on the loop is 0.2 meters. It's half of the diameter. When the car reaches point B, it is traveling at a speed of 3 meters per second. Calculate the value of h. Show your working. Okay, so I think we're going to have to use conservation of energy here. So we've got the following equation that we can create. So the gravitational potential energy at the top is equal to the gravitational potential energy at point B plus the kinetic energy at point B. Okay, because all your energy has to be accounted for somehow. Now, at the top of the hill at point A, we have mg times h, basically, because h is the height. And at the top of the circle, we have mg times the height of the circle, which is 0.4, plus kinetic energy at the top of the circle, that's half times mass times, how fast is it going? 3 meters per second squared. Cool, and our job here now basically is to work out what h is. Now notice that we can do something interesting. The m's cancel out. Okay, you can divide both sides by m, and they all go away. So really, h is equal to g times 0.4, so 9.8 times 0.4 plus half times 3 squared, but then we've have to have divided by 9.8, so all of that divided by 9.8. If we calculate that, let's have a look. So 9.8 times 0.4 plus half times 3 squared, or 9, and all of that divided by 9.8. 0.86 meters. I think that seems reasonable if the height of the loop is 40 centimeters, so it's 86 centimeters. There we go. Cool, so I'm happy with that, 0.86. Part B. Calculate the magnitude of the normal reaction force on the car by the track when it is at point B. Show you working. Okay, so when it's up here, you've got two forces acting on the car. You've got gravity pointing down, but also the normal force pointing down as well. And those two forces combined have to be equal to the centripetal force of your car, because it's in circular motion. So we have the following setup. We have force due to gravity plus the normal force has to be equal to the net centripetal force. Now we can replace a bunch of stuff here, so actually I'll solve for normal force because that's what we're trying to work out. So Fn equals Fnet minus Fg. Fnet is simply just mv squared on r because it's in circular motion. Fg is just mass times g, and we know everything here. So mass of the car, 250 grams, or 0.25, times v squared, I think it's 3 squared, so 3 squared over the radius, which was 0.2, minus 0.25 times 9.8. Yeah, all those numbers are good. Alright. So 0.25 times 9 over 0.2 minus 0.25 times 9.8. 8.8 newtons. C. Explain why the car does not fall from the track at point B when it is upside down. So this is a good question because it forces you to really think about how you're going to word it. So in order to travel around that part of the track at that speed, gravity is not enough to supply the entire centripetal force with what it's able to. So gravity alone is not enough to force it around in that circular path. It needs an extra push from somewhere, and that comes from the normal force that the track is applying on the car. I'm gonna just refer you, I guess, to the report because I don't want to waste time writing down a response. Where are we? So let's just have a quick read. Students were required to state that the centripetal force required for circular motion exceeds the weight force of the car. So that's what I was saying, like gravity is not enough to cause it to go around at that speed. This requires that a normal reaction force, which acts downwards, be added to enable the car to travel around the track at 3 meters per second. Some students chose to approach this problem by calculating the minimum speed at which the car could travel around the loop, which was 1.4. They then went on to explain how the stated speed was greater than this value, which meant that a normal reaction force would be present. The most common error was to indicate that this centripetal force exceeded the weight force, but not explain where the required extra force would come from. So yeah, there you go. Okay, refer to report. Sorry if my voice has gone down. My son's gone to bed, so I have to keep my voice down a bit. Question 9. A proton in an accelerated detector collides head-on with a stationary alpha particle as shown in the figure 9a and figure 9b. After the collision, the alpha particle travels at a speed of 4 times 10 to the 6 meters per second. The proton rebounds at 6 times 6 meters per second. Cool. Alright, so it's basic collision, right? Bang, and then they move off. Find the speed of the proton before the collision, modeling the mass of the alpha particle 4m to be equal to 4 times the mass of the proton m. Show you're working, ignore relativistic effects. So this to me just looks like a straightforward momentum question. So let's start by writing down a momentum equation. m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. Okay, now it's asking us to find the speed of the proton, which is, we'll call this, bloody hell, we'll call this m1 and this one m2. So find the speed of the proton before the collision. So we're working out u1. Okay, that's what we're trying to work out. So what is u1? So let's solve for u1, then put our numbers in. So u1 is equal to all this stuff on the left minus m2 u2. So m1 v1 plus m2 v2 minus m2 u2, all of that over m1. Now, we're going to be careful here because this is momentum. Momentum's a vector, so let's choose a direction to be positive. I'll just say to the right is positive. And so, if we input our numbers in, m1 is just m, mass of proton. v1 is the speed of the proton after collision, so it's traveling to the left now, so that's times negative 6 times 10 to the 6, plus m2v2, so m2 is the mass of the alpha particle, of 4m, times its speed after the collision, which is 4 times 10 to the 6. And this quantity here, m2u2, well, u2 is the speed of the alpha particle before collision, so it's not moving, so that term actually disappears, it's gone. And then we just divide everything by m1, or mass of proton, which is just m. And that's handy for us, because now that m cancels that m there, and also that m there. so it doesn't actually depend on the actual mass. So if we work this out now, we get, okay, so on the top we have negative 6 times 10 to the 6 plus 4 times 10 to the 6, and that's it. That's all we got. Whoops. Same over 1. So negative 2 million, 20 million, 2 million, negative 2 times 10 to the 6. That didn't sound right. What have I done wrong? Is it negative? Can't be negative because it's travelling that way. Where have I gone wrong, my friends? Okay, M1 V1 yeah, so negative 6 what have I done? Oh, I'm a silly duffer. There's a 4 here. I skipped that 4. Okay. So just 4 times 4 there. That's better. It's 1 times 10 to the 7. Alright, there we go. Okay, took me a second there. Cool. Alright, so I hope that makes sense. Sorry for my little brain fart. Alright, question 10. A projectile is launched from the ground at an angle of 39 degrees and at a speed of 25 meters per second as shown in figure 10. The maximum height that the projectile reaches above the ground is labelled h. Ignoring air resistance, show that the projectile's time of flight from the launch to the highest point is equal to 1.6 seconds. Give your answer to 2 significant figures. Show your working and indicate your reasoning. I don't know why it would say give my answer to 2 significant figures if it's telling me that the answer is 1.6. Anyway, whatever. Okay, so we're required to work out time of flight. Alright, so time equals don't know. But what do we know about the projectile? Okay, well, let's first of all split this initial speed into components. So that's, we'll call it just u. So this is ux, and that's going to be equal to 25 cos 39, and then we've got initial vertical speed uy, which is 25 sine 39. So I know the initial vertical velocity, which is 25 sine 39. We've got acceleration due to gravity as negative 9.8, and we know that at the top of the flight, its vertical velocity is 0. Alright, so TUAV, we want T, so it's V equals U plus AT, or T equals V minus U over A. V is 0, so we have negative of 25 sine 39 over negative 9.8, so the negatives will cancel out, giving us a positive time. That's nice. Alright, so we've got 25 times sine 39 over 9.8, 1.6. There we go. Matches what they're telling us it is. B. Calculate the range of the projectile, show you're working. Alright, so range. How far horizontally does it travel? Well, what we can do is assume that because there's no air resistance, it takes the same amount of time to go from the top back down to the bottom. So the total flight time is double this, so 3.2 seconds. So flight time equals 3.2. we know how fast it's traveling horizontally, which is 25 cos 39. So ux equals 25 cos 39, and therefore the distance traveled r, so just your speed, distance, time triangle. Okay, we want to know distance, so it's speed times time. So it's 25 cos 39 times 3.2, which is 62.2. Alright, there we go. Let's have a look if we are right. Okay, so there we go. First part, not too bad. It's just a normal Suvat equation. And then part B. Yep, given that students were given the time to the top of the flight is 1.6, they should have doubled this to get total flight time of 3.2. That's what we did. The horizontal range can be found using distance equals speed times time, where we're using the horizontal speed. And we got 62.2, they just got 62. It's all good. Go away. Alright, we might, how long is it? Okay, 57 minutes nearly, so I'll do one more question and then I'll break this into two parts again. Or maybe a couple more questions. Yeah, we'll stop at this page. So, question 11. What is the second postulate of Einstein's theory of special relativity regarding the speed of light? Explain how the second postulate differs from the concept of the speed of light in classical physics. Okay, so your postulates to relativity should be on your cheat sheet. The second postulate simply says that that the speed of light is the same. Stupid pen. Speed of light is constant regardless of the relative motions of source and observer. Okay, so it doesn't matter who's watching, doesn't matter how fast you're going, doesn't matter how fast the source of the light is going, whatever light you see is going to be traveling at c. Yeah, 3 times 10 to the 8. How does this differ from the concept of the speed of light in classical physics? Let me just say in classical physics, speed is additive, so that if we are moving towards a light source at v, the speed of light we measure would be our speed v plus the speed of light c, because you're moving like into the light. So that's kind of what I would state. What does the report suggest? Students can find a statement of Einstein's postulate in the study design, so you just copy them onto your cheat sheet. The speed of light has a constant value for all observers regardless of their motion or the motion of the source. So that's our first sentence up there. To explain how this differs from the concept of light in classical physics, students were required to explain that if there was relative motion between the source and the observer, then the measurement of the speed of light would vary. Specifically, if the source and the observer were approaching each other, the speed of light would appear faster than 3 times 10 to the 8 meters per second. And that's what we've said. So if we're moving towards the light at a speed v, then we would measure the speed of light to be our speed plus the speed of light. Or speed of light. C. Alright, cool. So that's that. We'll do this as the last one for this video, and then there'll be a part 2, or I guess part 3. Question 12. A sinusoidal wave of wavelength 1.4 meters is traveling along a stretched string with constant speed v, as shown in figure 11. The time taken for point P on the string to move from maximum displacement to 0 is 0.12 seconds. Calculate the speed of the wave. Give your answer correct to 3 significant figures. Show your working. Okay, so alright, I think the way to answer this is this second sentence here. The time taken for point P on the string to move from maximum displacement to 0 is that. So that means essentially the wave will travel, how can I put this? This part of the wave would move to here in that time, and this P would like fall down to meet that point, and that's how the wave sort of propagates. So it's basically the wave has moved a quarter of a wavelength in that time. Yeah. So a quarter of a wavelength is a quarter of 1.4. So how can I phrase this? Maybe just say it in words. The wave travels 1/4 of a wavelength in 0.12 seconds. And therefore the speed is equal to distance travelled over time. The distance it travels is 1/4 of the wavelength, so 1/4 times 1.4 over the time taken to travel that distance, 0.12, and that's going to give us a speed of, so 0.25 times 1.4 divided by 0.12, 2.92 meters per second. Alright, let's see if the report agrees with us. Ah, there we go, yep. So they've done it the other way around. They've said that the period of the wave is 4 times this part of the motion. So yeah, it's just another way of saying in that time the wave has moved a quarter of the wavelength. The time taken to move a full wavelength of the wave, that's the period, and that's why they're multiplying it by 4 there. Then they've gone and worked out the frequency, and then they've gone and used the wave speed equation, frequency times wavelength. They end up with the same answer. Yeah, but I hope that makes sense. Alright, we're going to stop this video here, and then we're going to continue with question 13 in the next part.